Alright, so before I go into the main part of the video, let me just start off with a quick intro. In other words, the history of the atom. The word atom actually comes from ancient Greek and roughly translates into indivisible, but you guys don't really need to know that stuff, so we'll move on to the more interesting stuff. In 1803, a guy named Joel Dalton came up with this idea of an atom, and it was literally just a ball. I don't know what kind of don this guy thought he was, but he's an idiot, so let's just move him out of the way. Alright, so then came in a real genius, Joseph John Thomson, aka my guy, J.J. Thomson, and then he discovered that atoms weren't indivisible as previously claimed. So he carried out experiments with cathode rays in a discharge tube and found out they were actually attracted to positively charged metal plates and repelled by negatively charged ones. Thus, the rays must have been negatively charged, and by then measuring the charge on those particles in the rays, he was able to deduce that they were 2,000 times lighter than hydrogen, and figured out basically what is called the electron. Well, electrons had to be in the atom, right? So, boom, there you have it, the plum pudding model. It wasn't long, however, until the real guy himself, Ernest Rutherford, came in and developed the atomic model even further with the discovery of the nucleus. Now, he didn't actually do this himself. In fact, Hans Geiger and Ernest Marsden did the most bits, but Rutherford did come up with the scattering equation himself. Rutherford also did discover alpha particles, which are positively charged helium nuclei, which was essential in the scattering experiment. Alpha particles are too tiny to be seen with a microscope, but Rutherford knew that alpha particles ionize air molecules, and if the air is within an electric field, the ions will produce an electric current. But let's find out how he actually did discover the nucleus. Alright, you ready? Boom. So basically, these lot got a radioactive source which emitted alpha particles. In this case, it was radium. This was then put in a lead block which only had one hole in a specific place, meaning the alpha particles could only exit the block in one direction in a particular straight stream, as, well, alpha particles can't penetrate lead. Furthermore, the whole experiment took place in a vacuum, so no external forces could act on the particles, and that the particles in the air couldn't affect the alpha particles. This stream of positively charged alpha particles was directed at a thin gold foil of roughly 2.1 times 10 to the minus 7 meters. Why gold? Well, gold is a dense metal that is malleable, extremely malleable. One can stretch gold foil until it is only a few atoms thick in places, which is not possible with aluminium. If the foil were too thick, then there would be no transmission of particles at all. The whole point was to demonstrate that most alpha particles pass through unchanged, and some of them scattered, which is only possible with a very thin foil. Alright, so these alpha particles were directed towards the layer, and most of them went straight through. Some of them were even deflected. You could tell if they were deflected or if they went straight through, as they hit a zinc sulfide screen. This zinc sulfide screen produced a bright flash, as the energy of the collision caused excitation and de-excitation of an electron, and as you know, that would produce some photons. Gegner counter. I can't pronounce the name, help. So this flash was seen with a microscope, and the whole experiment was done in the dark, and that flash was counted at different angles. With this method, a graph was produced. As you can see, the number of particles that deflected at a certain angle decreases as this angle increases. This did not match Thomson's plum pudding model, in which all the alpha particles should have gone straight through without deflection. Then, my guy the genius 9,000 IQ Rutherford, just like me, took these results and made an approximate equation for the number of particles that would deflect at a certain angle. How he derived the equation? Honestly, this made me hate everyone and everything for a little while. Not entirely sure why I did was correct, but I'm sure the Indian people on YouTube who taught me this will be very proud of me. So, here's to all the Indian people on YouTube. Firstly, let me derive the impact parameter and the distance of closest approach. So, the distance of closest approach is the minimum distance between the alpha particle and the nucleus. Alright, let's say for example a alpha particle is moving towards the nucleus and it's straight in front of it where the impact parameter is 0, but I haven't taught you the impact parameter yet, so we'll get onto that later. So the impact parameter is 0 and it's traveling straight in front of the nucleus. It will have a specific kinetic energy and 0 potential energy. There will be a point at which the force by the nucleus will cause that specific alpha particle to stop and deflect backwards the way it came. The point at which it stops is the point at which it has 0 velocity, and thus if it has 0 velocity, it has 0 kinetic energy. And because energy is conserved, that means its potential energy is maximum. That point is given as the distance of closest approach, and using Coulomb's law we can figure it out. The impact parameter is so much harder, oh god. Alright, so the impact parameter can be defined as the perpendicular distance between the gold nucleus and the direction of the velocity vector of the alpha particle when the alpha particle is at an infinite distance. Basically, when the force of interaction between the gold nucleus and the alpha particle is negligibly small. How to derive the equation for it? Please no. Oh god, kill me now. So we can firstly work out the change in momentum. Boop. And using the scattering geometry, we get this equation. A fairly simple one that we can work out using this diagram. Because there are two charged particles, Coulomb's law must be used to work out the force between the two. However, this force is only acting upwards. We need to find the force component along the change in momentum, and thus we can use F equals F cos psi, with F being Coulomb's law. Using Newton's second law, we know that force equals change in momentum over the change in time. Rearrange the equation for the change in momentum equaling force times change in time. Integrating on both sides will result in the momentum of the alpha particle. Now we need to substitute dt for the change in theta, as we don't want change in time, we want change in theta. So we can use angular momentum equation. When the particle is at the distance of r away from the nucleus, the equation is mr squared omega. It can also be written as mvb, where b is the impact parameter. Equating these two equations and then writing omega as d phi over dt will help us greatly. Alright, it's getting really long now, so if you're falling asleep, I don't blame you. Just rearrange the equation for d phi and substitute that into the momentum equation. Solve for the impact parameter and using the limits sine half pi minus theta, and boom! There you have it, the impact parameter equation. But there's more! If the mass is doubled, then P must also be doubled, and thus we can actually bring kinetic energy into the equation. And looking at this, we notice that that part right there is nothing but the equation for distance of closest approach, and therefore the impact parameter equals distance of closest approach over 2 cot theta over 2. Okay, now if we've done that, we can actually get onto the proper equation that results in Rutherford's scattering equation. Honestly, my face was just like this during the whole time, but who cares, let's get started. Let's start by getting the probability of an alpha particle that is being affected by the repulsive force. The effective area around the nucleus can be written as pi r squared, which can also be written as pi times the impact parameter squared. The number of particles in a specific area is the total number of particles over the volume, which is lowercase n. To work out probability, we can then use this n times by the thickness of the gold foil times by the effective area. And we've already worked out impact parameter before, and we can just sub that in. Now we want to work out the change in probability as the change in angle has occurred. And we can do that by differentiating the equation. Now we get onto differential cross-section, and here's a diagram because it's pretty much impossible to explain without one. This is really hard to explain, so bear with me. But the particles from the ring defined by the impact parameters b and b plus change in b scatter between the angles theta and theta minus d theta. Look closer. Notice there's a r sine theta and a r. That's the radius. We want to work out how the surface area of the ring is going to change as theta changes, and this equation is used for that. Using the double angle formula, we can actually change the equation to this. Now, to work out the number of particles deflected at a certain angle, we can use the total number of particles times by the change of probability all over the change in the cross section, because we know that it's going to be the same change in angle for all of the d thetas. Putting all the equations we have worked out into this equation will give us Rutherford's scattering formula. So what did we learn from this experiment? Number 1. Don't take physics at A-level or university. Number 2. Most of the space inside the atom is empty because most of the alpha particles pass through the gold foil without getting deflected. Number 3. Very few alpha particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. Number 4. A very small fraction of the alpha particles were deflected by very large angles, indicating that the positive charge and the mass of the gold atom were concentrated in a very small volume within the area, meaning this newly called nucleus is much more massive than the alpha particle. Whew! That's it really, to be honest. Rutherford came up with a nuclear model of the atom after this experiment, which was later developed by Bohr and others to come up with the current version of the atom. References.